welcome back. Probably many of you know Sebastian Velasquez, who was a postdoc here at IMPA a while ago, and now is a postdoc at King's College, and we will talk about Moduli or something. Please, Sebastian.
Good? Yeah. Well, first, thanks to the organizers for organizing this and inviting me to speak here. Congratulations, Fernando, for your birthday, your career. For me, when I had to choose about what to talk about, I had never given a talk about a work in progress, so I thought that was challenging. But at the same time, I had reasons to wanting to talk about this, and the joint work with Calum I'm going to talk about, which is somehow this. So around 2016, I had 3 important things happened at the same time. The first thing was I had my walk with Fernando through the forest. And the other 2 was that in that walk, I learned what a foliation was and what a moduli space was. So you can imagine how my head was when I got home. And well, I guess since then, for me, it's the people who I have talked math with know this foliation and moduli are very close in concepts in my head. It kept that way. So I'm happy to give this talk about this specific topic today. And so in Buenos Aires, we have spent a lot of hours discussing different spaces parameterizing foliations. A lot of hours comparing them. These spaces are, we have had some talks about them in this conference. And these spaces are essentially parameter spaces where you fix an x and you parameterize foliations on this x. If you have one foliation and that foliation but conjugated by an automorphism, in these spaces, these foliations are different. So what we have been working on is to do, well, part of it, I will try not to overlap with Calum. Part of it is interpolating this parameter spaces, as in also moving the x and quotienting by automorphisms. Yes? So we want to construct a good moduli theory for foliated pairs, I'm going to say. Yeah, so as Calum explained, there's apparently unavoidable reasons why we should work with birational geometry. All these examples Calum pointed at were to me at least, quite conclusive that you have to allow these singularities appearing in the birational theory of varieties and foliations. And at the same time, this thing Calum drew that was like, on the one side you have GIT, stable families. And I'm going to say non-JT. And the other thing is that essentially we have to skip this and go with a non-JT, which turns out to be the language of stacks, right? And so, to me at least, this combination of stacks and birational geometry at some points can get a little explosive in terms of how technical it can get. So what I'm going to try to do is I'm going to give an overview of all the machinery we are working with, and the plan, like the steps. We have to prove this and that, and we have proven this, but this is the hard point here, and so on. Yes? But first, before doing that, and also to show you how I at least, convinced ourselves that this was the right thing to do in terms of what the flatness condition should be, I want to do this exercise we did a lot in Buenos Aires of comparing the parameter spaces we already know and see what we like of them and what we don't like of them, and see how that tells us what our deformation factor should be, right? So we can describe foliations, one foliation, as one element like this, satisfying some local being locally decomposable, and integrable, and not having singularities in dimension 1. Right? We have at least one talk, two talks where this was mentioned. So the second one, which is, I guess, the favorite one of the birational geometers, like maybe, is pointing at the tangent vectors to a foliation, right? So this is going to be torsion-free of rank K. And this is going to be involutive. The third one, and this one is, I would say, has less work done on, but it's not less important, is something very close to what Fernando and Cesar told us, or Cesar told us that he was doing with Fernando in the first talk of the conference, which was, I'm going to do this just to, now this is rank K, and integrable, meaning that d of this, I'm going to be a little loose here, wedge this inside here, or omega high enough, and this is torsion free. There's a fourth one, which will be very important, which is far fields, right? Omega, this will be n minus k. For the moment, I haven't said much about what x is. We can say for now that x is smooth, or even normal or smooth. Both will work for any of these. And this will be, let's say x is smooth, and this will be a line bundle. This will be surjective in dimension 1. And the integrability and the local decomposability condition is that at a generic point, we'll have that phi equals the n minus k wedge product of a morphism like this. Well, this is a vector bundle. Okay, and this will be the local decomposability condition. And if you take duals, you can argue as in here, as in the vector, tangent vector way of describing foliations. Okay, so these are the 4 ways of describing foliations we have. We can also add, if we want, Fernando and Cesar's one, including FAF ideals, but I will not draw a picture of that. But so what are the spaces these things point at? Well, one points at a quasi-projective variety fk x l inside right? So because many are closed conditions and one is an open condition. And now 2 points at something, same thing, quasi-projective variety. So a subscheme of the quad scheme of Tx. If we require that the family is here, now if we put a relative version of this, that the normal sheaf is flat, this leads to a natural definition of this subscheme here, parametrizing integrable quotients of Tx, right? Flat integrable quotients of Tx. And on the other hand, we can do the same and integrable FAF ideal subsheaves. Three would lead to a quasi-projective variety. I'm not fixing any Hilbert polynomial here, so locally of finite type. Parametrizing foliations in this way, where again, if you put a relative version here, you just ask this to be flat and the same on the fibers. So what do we like and what we don't like of these things? The description of this one is nice, and also all these 3 of these have a natural compactification, which are like essentially taking closure or forgetting this thing here, or the torsion-freeness here. This one has a fixed line bundle, so that's a problem because line bundles may move. And also, well, what do have all of them in common is that in all of them, Kf is flat. Right? Because essentially you can compute Kf with these guys, and these are flat. Okay, at the same time, what we want, what we can see, and here I will cite a little of Fernando's work. So say in P4, you can get a component of, this is co-dimension 1 foliations here, which correspond to rational foliations, foliations that come as fibers of a map P4, P1, yes, and you have to fix the divisor, the degrees of the divisors defining this. So I'll do this, rational 2, 3, yes? So this is, you get, you put this F is with cubic or quadric and the cubic, yes? And this is an irreducible component. This is due to Fernando, Georgi, and Israel Vance.
Javier and Luis Neto before us.
Before, sorry, Javier and Luis Neto. Before Javier? No.
Javier and
No, Luis Neto, you, and Javier.
No, that's true. I was not born at that time.
Ah, I thought you were Javier, that Javier.
No,
Yeah. Sorry. That was okay. Inside here, we have a special foliation. You can view P4 as space of quartics on P1, and in that way you can act with SL2, right? And it turns out that I will write it loosely like this foliation. And so this foliation here has trivial tangent sheaf. So what happens on this other side? On this other side, well, first of all, something I didn't mention, but that's very important, is a result due to Qualbrun, sitting over there, that states that these two spaces are birational around the points where the singularities move nicely. I'm going to say they move flat, and flat depends on what co-dimension you are. It's a slightly different version of what flat means. But so in this point, that doesn't happen. And essentially, that doesn't happen because a general element here has singularities. So singularities here are co-dimension 2 plus points, right? So co-dimension 2 is the intersection of these two divisors and the points where the map has critical points, isolated. But here, you have co-dimension 2, and so this is co-dimension 2 plus co-dimension 2. It has two components of co-dimension 2. And so this failure of the singularities moving flatly turns out that correspond to that on this side, these two things are separated. Yes. So on this side, this guy is rigid. Rigid means now that all his neighbors here are conjugations of him. All right? So working with this and with this is very nice. You have a lot of structure. But then intuition fails because I wasn't expecting this. I was expecting this. Right? And you can do it the other way around. You can, in dimension 1, you can do the opposite. And instead of having something with free tangent sheaf, you can have something with that is an intersection of two foliations and have free this guy here, right? So this is to say it's not that this one is finer than that one. Both have the same problem to both sides. So maybe to sum up all this is I like the structure of this, but maybe flatness here is too strong. Because here we are asking the normal sheaf to be flat, and here we are asking the conormal sheaf to be flat. And these pictures are telling us maybe we shouldn't. And in particular, if we want our stuff to be compact, especially we shouldn't, because then what happens here? If you, right? That will stop you to being compact for a reason that you caused, right? Doing this choice. So, but this seems to be right, on the other hand. This is independent of everything. So we're going to keep this one and use this approach, the fuzz fields approach. And this is, after thinking of it a lot, I don't expect myself to explain, to be able to explain it because I thought of it too much. Now I kind of understand that this one is essentially, what we're doing is essentially this, but moving the line bundle. Okay, so how would that work? So flatness should be kf flat plus maybe something else. But now there's a lot of spoilers because Calum showed us what the something else should be, at least a necessary family of something else's we should add, right? So what should our Moduli functor have? So it should somehow include the pictures star, where star is the full picture here, or maybe here that I will not draw. Our intuition should be that picture. So have chances of being compact, at least not for our own mistakes in the choices. And be compatible with other deformation theories. Our deformation theories could be what we do here, for instance. This deformation theory, or this deformation theory, is compatible with, I don't know, deformation theory of sheaves, right? Because we can point at stuff. And also, if we allow the x to move, well, it would be nice if what we describe specializes to having, I don't know, the foliation, a unique orbit, which is the whole x. So as a particular case, deforming only x, right? OK, so now what's the definition first? Since Calum said we have to work with non-normal schemes. So a sheaf L on X is divisorial if there exists some Z of dimension greater or equal than 2, such that on the complement of this set, this is a line bundle. Okay, so if X is normal, this is being rank 1 reflexive. And the family of divisorial sheaves will be something like this, where L is flat and LT is a divisorial sheaf.
Don't you want reflexiveness or something?
No. At the end, if you want, we can add S2, which at the end will follow an S2 sheaf. On XT. Sorry, relative S2. S2 on the fibers. Okay, so with this, what's our deformation functor? We'll define our Moduli problem Mn dr which is on some t, this will be a I'm going to write the whole thing. So proper of relative dimension d kf kx is Q Cartier with its two fibers. Xt is semi-low-canonical. These are all on X, and Calum mentioned them before. And then we will have that now Kf is Q Cartier. Mkf plus Nkx is ample. And for every t, Ft is semi-low-canonical. Right, so we have we take the local stability definition on varieties, and we add our local stability definition on foliations. If we want, we can also add a Hilbert polynomial for the polarization too.
Sorry, what are you characterizing there? What are the objects?
Oh, sorry. You're right. And some phi omega r x over t to L, where this is a flat family of the divisorial sheaves. And this one, phi sub t, defines a foliation for every t. Thank you, sorry.
A of F is L?
F is the
foliation.
F is the, I'm going to say this, phi sub f. Yes, defines a foliation. So phi defines a family of foliations. F equal Ft. Like that.
Right, but then L, isn't L the canonical?
Yes.
Okay,
Yes, yes.
okay. So the condition of above is on L.
Yes. Yes. Sorry for that. It will make sense in a moment. My mistake will make much more sense in a moment, because what will the plan be to do this, to show that this is nicely represented? First, we'll have to embed it in something very, very big, with where L will not be Kf, will be just some L. Okay. 23, you said, Georgie?
23, yes.
Okay. Perfect. Okay. So what are we? What is the kind of theorem we want to prove? Is that we would like to prove, I want to have a theorem like this. M D R is a DM stack. This is what we want to prove, because then by Keel and Mori's theorem, we would get that M D R is quasi-represented by an algebraic space with some nice properties. what can we prove? Because of all the things Calum mentioned that we do have in dimension 1, we don't have, and some were close, some were a little more far away of proving. We do have is that MD1 and M is a DM stack. Separated DM stack in case someone has some definition. Okay, so how do we do this? Essentially, the plan will be first showing that this is an algebraic stack, and then showing that the inertia, the automorphisms, are finite. So every member of when you evaluate at a point that functor, every foliation appearing in that family in that functor has finite automorphisms. Those two together should imply that we have a DM stack. So one thing of all this is that if you look closely, they all have some sort of Grassmannian or some sort of quad scheme, right? And that is essentially what we will do too, but in a more stacky way. So first, some big family containing our objects and more stuff. Okay, so how we do this? Essentially, we rely on, as you may have perceived, we rely on a lot on what has been done for varieties. And in particular, we'll use that the stack polarized, which to every t assigns so this is proper, obviously flat, with a L, an ample line bundle. Is algebraic. Right? This here is an algebraic stack. There's a detailed proof of this in Stack's project. I don't know another reference for this, so if you know it, please tell me. And so why should we do this? Because we want to build a very, very big family of objects containing ours. So this being an algebraic stack means that there's a scheme. This is a scheme, P, with an arrow to the stack. And this is smooth and surjective. So all the polarized pairs appear in some ridiculously big scheme. And they are repeated over here. These are repeated modulo automorphisms in a smooth way. So the fibers of this map are smooth. But now we want to, now that we have this, what you would like to do if you were to do this, for instance, you would take a relative quad scheme of the tangent sheaf, right, here. And then you get a flattening stratification, and then you would end up with something like this, but in this setting. Instead of that, we have the problem that we cannot use quads because, sorry, I missed something very silly, but this map is, I'm going to say it, it's generically surjective on fibers. Like it's not zero on a fiber, yeah. But so it is generically surjective. It's not surjective. That's the point. So you cannot use quad scheme. So what do you use? Or there's a construction by Collar. There's the paper slash notes. It's also in his book. So the title is Hulls and Husks, and both are very important for what we do, but this one is the one we are using now. And essentially, a quotient husk for some sheaf f on x over t is something like this, where this is quasi-coherent. And its support has pure dimension, pure relative dimension, right? This thing here is very general, very general, both parts. But for instance, we are interested only in what happens here for rank 1, right? So there's a lot of simplifications we can do here. I'm trying to do them here too in what I'm writing. And so a family, if you have a sheaf on x over t, here we will have the sheaf omega r x over t. Right? This will be our pointed sheaf. We will look at all the husks. Something is called, this is generically surjective on fibers. Well, it's generally surjective. So a family of quotient husks is over some s to p, is you pull back the family x over t, you pull back the sheaf x over t, and you just construct another of these arrows now to a flat family of quasi-coherent sheaves, generally surjective on fibers, just as we were doing in the definition of our functor of foliations. So this is a husk, and what Collar proves is that the functor of husks, of quotient husks, I'm going to do this f, but it's an algebraic space. An algebraic space means that essentially, just as here we have a map from a scheme that is smooth and surjective, we'll have a map from a scheme that is étale and surjective and some even nicer condition. So what can we do with all this? Now we are very, very close. I'm going to do this. We have P polarized over P. We have quotient husks over omega r x over t. And this guy is an algebraic space, so it has some scheme. Here, this is étale, surjective. This is smooth, surjective. Okay, so we have this tower here, and this guy here has all the possible quotient husks of all the possible omega r x over t, right? So it's like immense quad scheme, but without the surjectivity condition. So what we'll do is, okay, what has this to do exactly with our Moduli functor? Well, our Moduli functor points at an ample line bundle, at a polarization, right? So we'll have something like this. And now, this was first, now second. Now I would like to define a map to this guy. But I can't, because there's way too much stuff here. There's stuff, for instance, of all the ranks. There's stuff where the G is not a family of divisorial sheaves. There may not be S2. And most important of all, even if they are, they will not be integrable distributions. They will just be morphisms. So what we have to do now is look at what we call local representability. Local representability corresponds to proving that we can essentially do what we do with flattening stratifications. So stratify this guy, and not fully, because as I said, for instance, integrability is a closed condition. So you will not take an open or something like that here. But you will get a locally closed subscheme of this guy parametrizing exactly what you want. So theorem, fifth. Well, how can I state this? If you have x over t, I will do this, omega. There is a locally closed partial decomposition Q, let's say locally stable to Q, such that a morphism for every S to Q. On Q, we have our, I'm going to write like this, the corresponding, the pullback family of husks is a family, it's a flat family of foliations or integrable distributions. If and only if S Q factors through the stratification, right? So like a flattening stratification, but a little different. A little different, essentially, because this says locally closed partial decomposition, and that means that you have a finite type scheme here, and it has a lot of connected components, and on each connected component, it is a closed embedding, right? I'm not saying that it covers the whole thing. That's the whole point. And that is essentially the key construction also for moduli of stable or general type varieties, nothing to do with foliations. Okay, so once we do that, I will change this by ls. So now our QLS is equipped with a family of nice foliations. So it will have an arrow to our moduli problem, right? And essentially, now that you set all these things together, it is easy to show that this here is smooth and surjective. Yes, essentially because this one was smooth and well, this was étale and surjective, and this is smooth and surjective. So this here will be smooth and surjective. Once you modify Q by the partial decomposition, now it won't be surjective. That said, it at least intuitively, it should still be smooth because the fibers differ by automorphism. So if you have something that defines a foliation, it will still define a foliation. If you have something that is a SU, it will still be a SU, and so on. So this is to say, proving that this is smooth and surjective is easy. Okay? And so this proves that this is an algebraic stack. And we still have to prove that it has finite automorphisms. Third. Well, I'll just state the theorem. So if xf is SLC, meaning is in our functor, and I'll just write the whole thing, kf plus mkf plus nkx is ample for some positive m and n, then the automorphism group of x and f is finite. I will not do a proof of this, but I will say that it follows from a proof of Lo Bianco. This is similar to Lo Bianco, Rousseau, Pereira, Georgi, and Toussaint, where they do something, a very similar statement. Instead of having ample, they have that a very similar condition, kf plus epsilon kx over f is big. Yes, and instead of SLC, they have that is epsilon log canonical. Right, right. Okay. And just to finish, I will say something else, which is what we are doing here is to construct a moduli theory that is somehow, even so, it has ideas, parts, definitions coming from another moduli theory. It's, at least I feel, it's somehow intrinsic. I don't, maybe you can formalize that, but in spirit it is intrinsic because when you want to prove separatedness, you need the semi-log canonical condition. When you want to prove this thing here, the local representability, you need the semi-log canonical condition. And also, well, for sure you need that the polarization is intrinsic to the foliation, right? Our varieties are not polarized anywhere, anyhow different than this. We don't know that, at least, right? So we are constructing a moduli theory that is intrinsic to the existence of the foliation. If you are okay with not doing that, you can essentially change this, the left side of the moduli functor, and say, okay, maybe I want to work with smooth foliations, smooth x, and ample kx, right? And then the ampleness doesn't have to do with f anymore, right? And that would mean that instead of, well, that to say, that, I mean, that moduli theory, smooth x and ample kx, is nice, has nice properties. So you could do the same, changing this guy for that other moduli functor. And everything would be easier because, for instance, that functor is separated. And if you are over a separated functor, then you're okay, right? That's all.
Okay, thank you. Questions, comments?
Perhaps it would be interesting to say something about the Chow rings or the Picard groups of these spaces. Do you think about that?
Yes, but there's yes, I plan to. Yes, we plan to. Is the
okay.
answer. But something I didn't say is that what do you say? Chow rings or Picard groups?
Or Picard, or
Yeah.
yes, all in
So
Picard.
there's the I don't know if I would be a little disappointed if it ended up here, at least for every D and R and so on, because you have a pointed line bundle, which is some determinant of this, of the push forward of this polarization. So you, in spirit, you could do the same that you do with MG and define, hopefully, an ample line bundle. So instead of being an algebraic space, it would be projective or quasi-projective variety. But that's for the next months.
Okay. Yeah, okay. Thank you. Good. Thank you.
The other half, yeah.
Thanks, Sarah. Great talk. You said you want to respect at the beginning that intuition from the parameter spaces of foliations that we. In which sense this one respect that part of separating the two components, you know, the components from the rational and the.
It doesn't. You don't want to do it. Because if you have in mind, well, that this was a psychological problem for me in PhD. If you have in mind that the foliation is what you draw, if you can draw it like a picture, then those things shouldn't separate. It shouldn't. So
Okay.
what you want to keep track of is be sure you're not separating them.
Ah, okay.
And essentially, from the point of view, if you want, you're in the smooth or normal case. Smooth maybe is easier. You are giving a twisted one form, if it's dimension one, moving continuously, just that. No extra flatness. KF is flat.
Okay. Okay, I get it. Okay. Thanks. And the other, behind all these stacked things and so on, is there any intuition in why this could get compact? Where's the compactness on this, or how to spec? Where is control? Or how to control? Where is hidden that part?
Calum?
Probably the limits that you come to
I can explain that, but off the records only.
that. Yeah, I'd say yeah. Probably as m becomes, or n becomes very large, it becomes compact. But for small values of m, it probably won't be compact, I guess.
Any further questions? We still have time.
Have you thought about some rationality properties of these moduli spaces?
Are there some gens to be rational, rational?
Like rational varieties.
Yeah, moduli space.
I'm tempted to say I don't expect it to, like the whole moduli space, because like in PN I don't expect it to, just PN. But there will have, I think a lot, there's a lot of things to do, but once everything works, one thing nice thing to do could be start translating all the things we proved in these other spaces to this space. I think a lot of them should translate. And so those components that are already rational in that setting, that have nice parameterizations and all that, maybe should be rational too.
Further questions, comments? Okay, if that's not the case, let's thank Sebastian again.